So welcome you back. So last few lectures we talked about invariant estimation. So what happens in many situations is the set of probability distributions which are under consideration, they have a very nice structure in the sense that if you apply certain group of transformations on those distributions, you remain in that class itself. And then if your loss function exhibits invariance, then this all suggests that your problem is invariant, so you should consider only invariant estimators. So your class of estimators under consideration has been restricted now. So because you are considering only the invariant estimators, the way you restricted class of estimators to unbiasedness, to unbiased estimators through the criteria of unbiasedness, here we apply the criteria of invariance and we restrict to the class of invariant estimators. Now there is a possibility that a best estimator among the invariant estimators may exist. Although the best estimator among the class of all estimators does not exist, there is a possibility that best estimator among invariant estimators may exist. Then we saw that if you have an invariant estimator and if your G bar acts transitively on P, that means any two elements of P are related through G bar for some G bar, then the risk of any invariant decision rule is not going to depend on F which belongs to P. So it will be constant. That further simplifies the things. That says that now you have to look for only these constant risk estimators and you have to find the estimator which has the smallest constant risk. So earlier in the case when risk function is not constant, then your risk function depends on F or the theta. And finding estimator which minimizes the function for every theta is generally not possible. So here it may be possible because the risk functions are constant for any invariant decision rule. So today we will deal with one particular kind of invariance which is called the localization invariant estimation. So the situation is as follows. So suppose you have a data which is x1, x2, xn. So this has a distribution function f theta x, which is of the type f of x1 minus theta, xn minus theta. So this theta is same for all the n components, x which is x1, x2, xn belongs to R. And suppose my theta is in capital theta, which I take for the time being whole real line. So what is the class of distributions over here? My class of distribution. So here this f is for some specified distribution function f. So note that here x has a distribution function f theta. This functional form of f is known because f is specified to you. But through introduction of these thetas, this f theta x, although the functional form is known because the functional form of f is known, but it has unknown parameter theta associated with this. So this is a situation where we are talking about a parametric statistical inference. So what is your fp? P over here is f theta. Theta belongs to capital theta. So this is your set of probability distributions under consideration. So what I assume is suppose f is the PDF corresponding to this specified f, which is over here, then class of PDFs is, which we are considering is nothing but P star, which is f theta. Theta belongs to capital theta. And what is your f theta of x1, x2, xn? Because distribution function is this, so you can talk about taking its derivatives to x1, x2, xn. So it would be small f of x1, x2, xn because small f is the PDF corresponding to capital F. So this would be nothing but f of x1 minus theta, xn minus theta, and x is in Rn, theta is in theta, which is nothing but my whole R. Now, let me just spend a second on why we call it as a location invariant estimation, because here I am dealing with the location family. What is a location family? Location family is because of the fact that if x has a distribution f theta, then f of x1 minus theta. So location family means it is because if x has a distribution function f theta, this implies that x1 minus theta, xn minus theta has a distribution function g which does not depend on theta. Why? Because in this case you can see that g of x1, x2, xn, I have to see that it does not depend on theta. So g of x1, x2, xn is nothing but probability that x1 minus theta less than or equal to x1, xn minus theta less than or equal to xn, which is same as probability that x1 is less than or equal to x1 plus theta, xn is less than or equal to xn plus theta. When x has a f theta, was it a distribution function of x1 and x2, xn? Each argument is subtract theta. So that means it is a distribution function at the point x1 plus theta, xn plus theta. When x has distribution function f theta, that means what I have to do is I have to put it f over here, and I have to subtract theta from each of the arguments over here. So if we subtract theta, it is nothing but x1, x2, xn. So it does not depend on theta. No theta. So it does not depend on theta. And that is a reason why it is called a location family. Of course, one can talk about scale family also. In that case, exactly the same thing happens. If x has f theta, then x1 upon theta, xn upon theta should have a distribution which does not depend on theta. And such a situation is called location family, which we'll be considering in our next lecture. So these are location family. Now, what I have to see? I have to find suitable group of transformations under which my P is invariant, or corresponding PDFs P star are invariant. Now note that if I make a transformation x1 plus c, xn plus c, what would be the PDF of x1 plus c, xn plus c? Because if I put x1 plus c as y1, the PDF here would become y1 minus c minus theta 1, yn minus c minus theta, and you are again in the same scenario. So it looks like a suitable group of transformations here would be GC, such that C belongs to R, and GCX on the sample space. So GC of x1, x2, xn is nothing but x1 plus C, xn plus C. X belongs to Rn, and C belongs to R. So you have a group of transformation. Basically, these are additive group of transformations. We have seen that this is a group. So if x has distribution function f theta, GCX, which is x1 plus c, xn plus c, has a distribution function what? Anyone? So you can see what you have to do is you have to find out a distribution function of x1 plus c, xn plus c, which is same as probability that x1 plus c less than or equal to, let us say, t1, xn plus c less than or equal to tn, which is nothing but probability that x1 less than or equal to t1 minus c1. Sorry, I have to put the same c, because I cannot take the different c's, because my group of functions is gc, where c is in R, and I am applying the same c to each of the components. So x1 less than or equal to t1 minus c, xn is less than or equal to tn minus c. And what is this? This is a distribution function of x1, x2, xn at the point t1 minus c, t2 minus c, and tn minus c, and distribution function of x1, x2, xn at the point x1, x2, xn is nothing but just subtract theta from each of them and apply f. So this is same as f of T1 minus C minus theta, Tn minus C minus theta, which is nothing but f of T1 minus C plus theta, Tn minus C plus theta. So what happens? Distribution is again of the type f of T1 minus some common C plus theta in all the components. The only thing I have to make is C plus theta is in the parametric space. Now, if x was in f theta, so this theta is in R. If theta is in R, C is in R, so C plus theta would also be in R. So this quantity is in R. So what happens? I am again in the same family. My distribution function is again of the type f of x1 minus some theta, xn minus some theta, except that theta now gets transformed to C plus theta. So this implies that my P is invariant. So P is invariant under G. Now this G induces a group of transformation on the parameter space theta with the corresponding induced group of transformation on the parameter space as G bar C, C belong to R. So what was happening? This GC, which was on the sample space, gives me C plus theta in the parameter space, because GCX has distribution function f of T1 minus C plus theta, Tn minus C plus theta. So what is G bar C of theta? C plus theta. So what I have to do? So my P is invariant. So the problem would become invariant if my loss function is also invariant. But for loss to be invariant, I have to first guess what should be the appropriate group of transformations on the Xn space. First, let us see what is an Xn space. Actually, in this problem, my goal is to estimate this theta. My goal is to estimate this theta. So my Xn space A, in this case, because I am estimating theta, so my Xn space would be same as the space of possible values of theta, which is nothing but capital theta, which is same as R. So I have to see what is a induced group of transformation on the Xn space. So you see what is happening. GC changes C to C plus theta. So what should have happened to the Xn? Xn should also change by C. So my Xn A should be transformed to C plus C. So that suggests that my G tilde, the induced group of transformation on the Xn space, should be nothing but GC tilde, C belonging to R. And what is GC tilde A? Is nothing but C plus A or A plus C, where A is in Xn space and C is in real line. So first I assume that my loss function is L theta A. So remember that my goal first is to estimate theta. To estimate theta under the loss function L theta A, where theta is in capital theta, A is in the Xn space. So I'm interested in estimating the location parameter theta. Now for convenience, because we have seen that I would generally expect a good loss function to be convex in A, because it gives minimum at A is equal to theta, and as you move away from theta, L theta A increasing. So I have assumed that this is convex in A for every theta belonging to theta, because those are the reasonable loss functions. So L is, so my problem would be invariant provided L is invariant. This is quite general loss function. So I try to make this loss function invariant. Let us try to see what are the kind of loss functions which would be invariant under G. So L theta A is invariant under G if and only if. What happens? Loss in estimating theta by A should be the loss should be the same in the two problems. In the original problem, theta and A were the parametric point and action space. What are the corresponding points in the second problem? Theta goes to C plus theta. So this loss would be same as loss in estimating C plus theta by the corresponding action, which is nothing but C plus A. For every theta belonging to theta, A belonging to A, which is a real line, and C is in R. Now this is equivalent to saying that L theta A is nothing but I choose C to be minus theta, because this happens for every theta belonging to capital theta, A belonging to A, C belonging to R. So for any fixed theta, I choose C to be minus theta. So if I choose C to be minus theta, it becomes L0 A minus theta. If this holds, then this holds, and any loss function which satisfies this has to be of this type. So that means this is only a function of difference of A and theta. So I can call that as W of A minus theta. So what does this suggest? A loss function L theta A is invariant if and only if it is of the type W of A minus theta for some function W. So we write down that. So L theta A is invariant under G if and only if L theta A is same as W of A minus theta for some function W from real line to real line. In fact, I will take W to be non-negative. So from real line to 0 to infinity. This is just straightforward to see, because one part we have already seen, that if my loss is invariant, then it would be function of only A minus theta. So if L is invariant, then this would be of this type. Now suppose L is of this type, then I have to see whether L is invariant or not. So I have to see whether L C plus theta, C plus A is same as L theta A or not. So I apply C plus theta, C plus A, it becomes C plus A minus C plus theta, C gets cancelled, so again you get W of A minus theta, which is same as L theta A. So L is invariant under C. So we assume that L theta A is same as W of A minus theta for some convex function W from R to R. Now note that if W is convex, then L theta A, which is W of A minus theta, would be convex in A for every theta belonging to R. If you want to see an easy proof, you just take the double derivative, provided W is differentiable twice. So with respect to this double derivative with respect to A would be W double prime A minus theta. But if W is convex, W double prime is always greater than or equal to 0. So I assume this. Now, by considering only convex loss function, I have made my life simple, because we have seen a result which says that if your loss function is convex in A for every theta, then you need to consider only non-randomized decision rule or non-randomized estimator. So this says that it is enough to consider only non-randomized So my problem is invariant under G, because I have seen my P is already invariant under G if I am in the location family. And if my loss function is of this type, then my loss function is also invariant under G. So under the given setup, my problem of estimation is invariant under G. So I should consider only the invariant decision rules or invariant estimators. Not only that, because my loss function is convex in A, so I should only consider invariant non-randomized decision rules.